All right, so I'm very grateful and honored to introduce our next speaker, Professor Lars Hansen. He is David Rockefeller Distinguished Service Professor in Economics and Statistics at the University of Chicago. He is a leading expert in economic dynamics and works at the forefront of economic thinking and modeling, drawing approaches from macroeconomics, finance, and statistics. He is the recipient of 2013 Nobel Prize in Economics. Professor Hansen has made fundamental advances in our understanding of how economic agents cope with changing and risky environments. He has contributed to the development, of course, many statistical methods that we all have used to explore the interconnections between macroeconomic indicators and risk in financial assets. The Nobel Prize Committee recognized his work in this area, which has been used to test theories and models that have shaped our modern understanding of asset pricing. His recent research explores how to quantify intertemporal risk trade-off and ways to model economic behavior when consumers and investors struggle with uncertainty about the future. Improving models that measure risk and uncertainty have important implications, of course, for financial markets, fiscal policy, and macroeconomy. I'm delighted that he accepted our invitation to share his most recent research with us. By the way, Lars and I have a longer connection. Our sons are classmates and good friends doing their PhDs at MIT. So Professor Lars Hansen talk is titled The Impact of Geoscientific and Economic Uncertainty of Climate Change on Social Valuation. Lars, the floor is yours, and thank you very much.
Well, thank you very much for that introduction. Let me see, I can execute screen sharing here. Is this good?
Yeah, it's working. We can see it.
Okay, good. Well, thank you very much for this opportunity. What this is about is thinking about uncertainty and bringing to bear asset pricing type methods to think about social valuation. And I'm going to be talking today about challenges connected to climate change. So I have some collaborators on this, Mike Barnett, who's at ASU, Buzz Brock, who's at Wisconsin, and we have connections to some geoscientists I'll talk about a little bit later in this lecture. So what is the challenge here? So the human impact on the environment, there are reasons to believe that it's not internalized correctly by markets. And thus the social cost and private cost may not be the same. So this is a case in which there's a so-called externality. Now, there's two sources of uncertainty that come into play in thinking about how to measure the social costs. One comes from the geosciences. So CO2 emissions today impact the future climate. There's lots of evidence of the human impact on climate, but the quantitative magnitudes and time horizons in which it plays out is where the uncertainty is. So economics, climate change, we conjecture will certainly alter future economic opportunities as well as social well-being. But again, there's substantial uncertainty to thinking about how that is. This latter type of uncertainty is not something that's that easy to tease out of evidence. And I'm going to argue that these two sources of uncertainty kind of interact. There's a sense in which they're multiplicative, and it's important to think about them simultaneously instead of separately. Now, what we're aiming here is a computationally tractable laboratory to explore subjective uncertainty, and including potential model misspecification and ambiguity across models. So we want to, the goal is to assess the impact of this uncertainty on climate policy outcomes, and the way things work is you try to isolate the forms of uncertainty that are most consequential for these outcomes. I like to think of this as quantitative storytelling with multiple stories, Each model provides us with a story that we can use to interpret the data to make policy recommendations. We've got multiple stories on the table and we need to evaluate them. So this is a type of uncertainty quantification, but it's not the usual type that's done in the sciences where we, because we really put the question at hand right on the table and use that to kind of guide where we think the uncertainty components are most impactful. So where does asset valuation come into all this? So we know from asset pricing theory that tells us how markets assess investment opportunities in the face of uncertain future net payoffs. What does asset valuation provide for all this? So we know asset pricing theory tells us how markets assess investment opportunities in the face of uncertain future net payoffs. So as a macroeconomist, I like to think about these assets in broader terms than just financial assets, including physical, human, organizational, and even environmental capital. Associated with each of these assets is a prospective set of net payoffs to investments. I want to apply these same type of insights to social instead of market valuation, in which we'll be thinking of the corresponding valuation of social cash flows, potentially negative cash flows because of damages to the environment and to the economic opportunities. So let me talk about the social cost of carbon. This is commonly referred to in policy discussions, and unfortunately its meanings and targets and measurements have been different across applications. Pre-Trump, they used to post numbers about the social cost of carbon, but if you kind of dug into the measurements, there was, well, at least in my case, kind of a lack of clarity and coherence in terms of what they meant and how they're constructed. But there is a way to do it coherently, and we'll be doing that here. We're going to use a well-posed version as an analytical tool to assess the impact of uncertainty. So, as I indicated, we're thinking here in terms of an externality. A carbon emission alters the climate. This, in turn, impacts economic opportunities and social well-being in the future. The social cost of carbon includes the socially efficient Pigouvian tax on carbon emissions that corrects this externality. So from a policy standpoint, so far this might look like pie in the sky. Yes, we can invent this. We could figure out how to implement these Pigouvian taxes, and that would fix everything. And I would agree that that's pie in the sky. We're using this as, but we're going to use this as kind of an interesting economic metric to assess the importance of uncertainty. How much does uncertainty affect this hypothetically correct social price of carbon? The social cost of carbon is an asset price. The social cash flows of interest are basically nonlinear response functions with two interconnected contributions. Geosciences. It's going to tell us how a change in CO2 emissions alter the temperature in the future. And we're going to bring to bear evidence on that. Economics investigates how changes in temperature will alter economic opportunities in the future. Now, what the social cost of carbon does is take these kind of two interconnected contributions, figures out a corresponding social cash flow that's in some sense a convolution of these two, and uses stochastic discounting and then adjusts for uncertainty. So as a way to represent this social cash flow, this social cost of carbon as an asset price with a social cash flow attached to it. And that's the perspective which I'll be adopting today. Now, I believe it's very important to confront policy uncertainty. And at the outset, I want to mention here a tension. There's, I think, kind of undeniable limited understanding in the mechanism by which policies will influence economic outcomes. As I indicated, we have this geoscientific uncertainty, which I'll show you some evidence for. We also have uncertainty about the resulting economic damages and how economies will adapt and the like. So this is just, I think, a kind of a basic scientific fact that we have a limited understanding of these mechanisms. On the other hand, there's a demand for precise answers by the public and our government policymakers. Typically, if you want to influence the government or government policymakers, you want to go in with great confidence to say, well, here's what we ought to do and why. And once you acknowledge the uncertainties attached to it, then there's some concern that, oh, well, you'll just lose your influence. So that's the tension I see. Okay? And this going in with great confidence, though, excessive confidence has its own cost, I would argue. I find them documented in a very interesting essay by Hayek. Hayek, when he won the Nobel Prize, had to write this essay. You're supposed to write an essay explaining why you won the Nobel Prize, which pretty much nobody really does, or very few do, because it gets boring. Hayek, who just won the Nobel Economic Prize in Science, writes an essay on the limited extent to which economics is really a science, it's a very intriguing read. There's lots of it I don't fully embrace. He's very, very hard on the field of econometrics, as we basically learned very little from it over long horizons. But there's a statement in here that I think is very relevant to the type of questions I'm trying to address today. Even if true scientists should recognize the limits of studying human behavior, as long as there's people out, as long as the public has expectations, the people that rise to the occasion and pretend or project themselves as more knowledge than really is true in order to meet this popular demand, and that's the worrisome here. So, for quantitative policy analysis, how should we acknowledge the limits to our understanding? Now, one of the fears of kind of putting uncertainty out there is the concern that, well, maybe a policymaker will come back and say that since we don't understand things fully, let's just do nothing and wait till we understand things. And that's really not what decision theory tells us. Decision theory tells us the possibility about bad outcomes can be enough that we may well want to act today. We don't need to know that those consequences for certain. And so so the hope is by putting that out there, we can start having a much more accurate and honest assessment of knowledge and its impact on policy. So where does uncertainty emerge? And this, like in a bunch of previous work I've done in trying to get better understandings of uncertainty and markets and the like, I want to think about uncertainty in much broader terms than is typical in economic analyses and typical in economics classes as we teach them. So I mentioned this term before, quantitative storytelling with multiple stories. So let's kind of work our way there. So let me start off with risk. I'm building on a categorization in part from Knight, but Knight's writings on this while intriguing were not the most coherent. But I'm going to start with risk. So for me, risk is uncertainty within a model. Each model, if I write it down, it has random impulses, and and the model tells me probabilities. It doesn't tell me outcomes, but it tells me probabilities. That's risk. So we talk about risk aversion when we talk about risk premia under rational expectations. That's the perspective we're taking. So now let me put on the table ambiguity. There are multiple models on the table, maybe unknown parameters, unknown model specifications. Each model gives rise to a story. It's a story about implications and for both policy and empirical evidence and the like. How do we weight these alternative stories? Of course, we're all exposed to kind of Bayesian decision theory and Bayesian statistics, and that gives us this kind of beautifully elegant way of how to update subjective probabilities. But there's still the subjective uncertainties that can be very important right from the outset. How do we gauge and set those? In these climate change type problems, learning, I would argue, can actually occur very, very slowly. That may change when we have even more dramatic climate effects. Maybe we'll suddenly start to learn quickly, but by then the action may be incredibly costly. Finally, misspecification, and this may be the hardest component of uncertainty to wrestle with. The models we write down in macroeconomics and essentially most of our financial models, they're wrong. They're abstractions. If they were full descriptions of reality, they probably wouldn't be very useful. That's not what their intent is. But so given they're wrong, but hopefully insightful, how can we use them in sensible ways? How can we make sure that the mistakes where the models come up short really are not harming us in terms of the type of actions we're thinking about taking. So I want to think about uncertainty in these much broader terms, and there's at least attempts or ways to think about these different components. So let me talk, roughly speaking, about navigating uncertainty in this broader environment. So we want to use probability models. We don't want to throw them out. We want to use them, but accept the fact they're misspecified and accept there's ambiguity as to which among the models which we want to use and which is the best one. So the aim here is you want to use models in a sensible way rather than just throw them out. We don't want to give up the tools of probability and statistics, but we still want to use them to kind of limit the types of, the amount of uncertainty that's entertained. Now, just like risk aversion is a theory of caution, more generally, uncertainty aversion is kind of a dislike of this uncertainty about probabilities over future events. And there's issues about how averse we ought to be to this, and that, of course, will have implications for how we design policy. The implementation of this can become quantitative, and you kind of load in these different uncertainty components, and then you let the actual aim of the model, as well as the models, as well as the model computations, to help you target the uncertainty components that have the most adverse consequences. So it's kind of a very structured sensitivity type analysis you're doing here. You go over the typical subjective inputs. This could be subjective probabilities. You go over the potentials for model misspecifications and figure out where things are most consequential. And so this allows you to take a high dimension of uncertainty and collapse it down to something that's much, much smaller. And that's the whole aim of these methods. And the decision theory gives us a coherent way to do this. So the decision theory I'm going to use, has to be dynamic or recursive. For the models I'm talking about today, I'm going to do them continuous time as diffusion models. That's not critical to the overall agenda, but that's what I'll be doing today. And there was some debate about how to do this in taking these continuous time limits, which Miao and I addressed in a previous paper, in which we produce a recursive implementation of what's called a smooth ambiguity model in continuous time. Smooth ambiguity model is a way to confront this ambiguity across models. Discrete time versions were originally axiomatized by Klebanov, Miranacci, and Mukherjee, and as decision theorists do, they debate axioms, and there's other axiomatic discussions about this. I'm not going to get into these. But basically how this is going to play out is we're going to have, in these dynamic models, we have ambiguity about the local mean specification. We'll appeal to this axiomatic defense for differential aversion to ambiguity over models in contrast to aversions over risk. But we're going to exploit this equivalence between what I'm going to call a smooth ambiguity model and a robust choice of priors. So I'm going to interpret this instead of as kind of a robust Bayesian method where we are doing some type of formal prior sensitivity analysis. And then there's an additional adjustment, which I'm not going to be focusing on in the computations today, but there's an additional adjustment that can be made for model misspecification, model by model, using some results I've done previously with Sargent and others. So the formal approach is for us, you take a single agent decision problem, and then you change it to a two-player so-called zero-sum game, but it's a dynamic one, stochastic, recursive, and the like. So for a planner, the one player is a fictitious planner engaged in maximizing social well-being. The other one is trying to investigate the consequences of uncertainty. So in order to work out these bounds and figure out where things are most consequential, that player engages in a form of minimization. It can be minimization over probabilities, over potential misspecifications, and the like. For actual calculations, we're going to use kind of Kullback-Leibler type metrics, relative entropy to bound probabilistic uncertainty. And then which would be basically solving models with PDE methods along with extra twists for computations. Now for the purposes of today, and to keep things simple, I'm going to have this single social planner. But in fact, one can imagine more generally, there's these issues about the planner uncertainty, the private agents uncertainty, the investor uncertainties. They can be different, and there's kind of and then one can put additional interactions here between the private sector and the government. So I view that as very important. But today I'm going to simplify it to think about a fictitious planner facing uncertainty, and then figuring out what the implied social cost of carbon is. So how do we adjust for uncertainty and valuation? So here I want to borrow very much from the ideas of option pricing. We want to do this in kind of a probability measure approach. We're going to take this two-player game, and then we're going to the minimizing player is going to be choosing probabilities. These probabilities are going to give rise to the outcome of this. Will be a set of probabilities that one can show are the ones which you want to use to engage in valuation. So these are going to be probability adjustments made, that these are great changes in probability that capture these uncertainty adjustments for ambiguity, for misspecification concerns and the like, as they show up in the social cost of carbon. So just like in option pricing, we'll be able to reduce these uncertainty adjustments to a change in measure, and this change in measure is going to be making these uncertainty adjustments for us. And this is going to be shown formally. So let me just add a little bit of detail on this. I'm going to have to, because of shortage of time and the like, I won't be able to go probe in any great mathematical detail. But imagine that we've got a state evolution equation. Xt is the state vector, At is some type of decision process, or A is a decision process. The decision process could affect the drift, it could affect volatility and the like. Now we're going to be looking at changes in probabilities that are consistent with the so-called Grassanov transformations. And our changes, our uncertainties about models can be translated into that. Our uncertainties about potential misspecifications can as well. So that corresponds to taking what we start off as being a standard Brownian motion and changing its distribution, as we know from Grassanov. Under the altered distribution, then there'll be a so-called drift distortion that shows up and is present. So this is going to remain a useful way to represent these types of uncertainties which we're facing. Now for misspecification, we go inside a Bellman, some type of Hamilton-Jacobi-Bellman type of equation, and then we kind of look at how I'm missing a term in this equation. Oops. Anyway, we're going to go inside that equation, and then when I think about how changing that drift is going to interact with the partial derivative of the value function. So the key term here ought to be sigma of xa times ht. So you'll be so locally you're just solving a quadratic minimization problem, and the minimization problem then is going to kind of, and the C sub m is kind of govern how much concerned you are about model misspecification, and so that's going to give rise to a drift distortion. As I say, apologies for this equation. It's not quite the right one, but the bottom line is this is locally a quadratic equation, and then the choice of h then will be will depend on actions, it'll depend on states and the like. Now we're also going to do this adjustment for uncertainty over models. I'm going to be putting multiple models on the table. I'll be doing that in a few minutes. Again, I apologize for a typo here. There's inside the mu sub x should be a theta. The theta is going to now affect the drift. There'll be multiple specifications of the drift going on here, and then we have some type of probabilities attached over that. This q sub t over theta, and that can be updated based on past information. And so instead of taking expectations of this drift, I'm going to be taking this log exponential adjustment. And so smooth ambiguity is basically that you form some certainty equivalent over this, locally over this drift, because the drift itself depends on unknown parameters. Now the smooth ambiguity is we're going to think of, we want to kind of open the hood of smooth ambiguity, and hopefully the notation here improves. So the actual correct formula, this has the theta in it, as it should. for the smooth ambiguity. And it turns out that that can be the outcome of a robust prior posterior type calculation. Now in a dynamic setting, I'm never quite sure whether to call this QTs, priors, or posteriors, because today's posterior is tomorrow's prior. So I mean, it's but anyway, the Q sub t is capturing the information I have about the current parameter. So what I'm going to do is I'm going to solve a minimization problem subject to penalization. I'm going to have this Kublak library type form. Think of G of theta as some type of relative density over the over the potential probabilities, and I'm going to adjust this original Q sub t in a robust way. Okay, so I'm going to say, well, Q sub t is my best guess at these subjective probabilities, but I'm not that confident in it. So I'm going to look at changes in it. The changes are captured by this G. So as G is going to integrate to 1 against Q, in that sense, is a relative density. If I solve that problem, two things come out. First is this implied change of probabilities are going to say that this, instead of using Q sub t, you're going to take Q sub t and scale it by this exponential tilting term, adjusted so it's a density. So and the exponential tilting depends on the drift as a function of the unknown theta. So this is this conservative adjustment you're making for the subjective uncertainty, for the subjective inputs, QT of theta. Now I've substituted in the maximizing decision process in this, because when I'm actually doing the adjustment for uncertainty, here I'm going to be using a probability, and this is going to be the probability. This is going to give rise to the probability I use to adjust for the uncertainty once I evaluate that at the corresponding decision process that comes out of it. So anyway, this partially, this I find very useful. This kind of robust Bayesian interpretation I find very useful for addressing this ambiguity of our models. Okay, let me return to this social cost of carbon as an asset price. So roughly speaking, we can think about forming a nonlinear impulse response of emissions today on damages in the future. Now we need to incorporate margin utility adjustments, as you typically do. Typically, there's going to be interacting uncertainty between economic damages and climate change. And then we'll do stochastic discounting, but under this uncertainty adjusted probabilities that they'll both accommodate the ambiguity and model misspecification concerns. Okay, to do all this, remember here we're computing the social cost of carbon. There's sometimes in the environmental economics literature, they want to run the market prices. The way I've laid it out here, these are market prices. These are prices that would, at so-called efficient allocations. They're shadow prices at efficient allocations. And they're not necessarily those observed in competitive markets. One could do things, one could do a local policy analysis at the competitive market prices and make a kind of a local justification, but that would be an alternative way to go to use very similar tools, but that's different than what we're doing here. That would not give us the social cost of carbon, but it would help us to assess small changes in policy. So now let me talk about the economic modeling framework in order for us to do the calculations. I'm going to start off with a fairly standard macro type model, modified a little bit. So in the simplified model, I think of this as so-called AK model with adjustment cost. I've got capital, there's investments, there's adjustment costs and investment. I take the capital and I get output that goes into consumption and output that goes into investment. The consumption then shows up in quote the utility function of consumers and therefore affects well-being. Now I'm going to change that. I'm going to put in exploration. I'm going to allow for some of the output to be involved in an investment in exploration that then allows us to enhance the stock of reserves. And then from the stock of reserves, I'll draw out emissions. And so, I like to drive my car. The like that emissions are going to show up as contributing to a social well-being. Now, if I ran this economy, not talking about climate change, this would be an economy where there'd be kind of a nice stochastic growth path, emissions would grow, we would potentially fry the economy because of this, because we've ignored this externality. So now I want to put in climate change. At the same time, these emissions are affecting the climate. The climate through damages then are affecting productive opportunities or well-being. This is the externality part of this. And this is why, you know, social and private, there's this wedge between social and private. So formally, I'm going to imagine I'm going to have some type of forcing process that's evolving like in a diffusion that's exogenously specified. Here's my production. I'm going to have a capital evolution process. For the purposes of today, the mu k of z is just going to be constant. I'm going to have this adjustment cost on investment, and then there's this these stochastic returns to investment. Production then gets split between consumption, investment, and this JT. This J is this investment in the discovery of new fossil fuels. So I'm going to put another sector in this economy. There's a stock of reserves. The stock of reserves is going to evolve as follows. So you can draw it down by through depleting the resource, emissions, but you can also expand it by investment. And I'd arrange it to be homogeneous of degree 1. The well-known hoteling model of a fixed capital stock and reserves is a special case of this, where psi sub 0 is equal to 0. And there's just a fixed stock of reserves, which you then draw down. We pushed away from that because of this expiration. Okay, economic impacts on climate change. So climate change can impact social preferences. They can impact production possibilities, and they can impact growth potential. There's empirical evidence on the growth potential. There's reasons I don't really trust that evidence at all. When we ran through our calculations, we got incredibly huge social cost of carbons, but their numbers I don't take very with much seriousness at all. So I'm not going to show you those numbers, just because we don't yet have any credible impacts or any credible inputs for how to measure this growth potential. But the first two, in the context of our model, can be basically treated mathematically the same. And so that we can go back and forth between the first two interpretations. So I'm going to adopt, for the temporarily, a simplified model of climate dynamics. I'm going to fill in the holes of this in a little bit. The climate literature suggests an approximation that simplifies model comparisons. Climate models are highly complex, and there's a bunch of them out there. There's no way we can embed a whole bunch of climate models inside an economic model and have anything that's remotely tractable. The climate models themselves are very, can be hard to solve. Often they have kind of spatial components to them and geographical components, and they're near chaotic or chaotic or near chaotic dynamics and the like. So there's no, that's just not a promising avenue to just plug those inside economic models. But what climate scientists have done is they run experiments, emissions different scenarios, or say through the different climate models, or kind of carbon concentration scenarios, or carbon in the atmosphere concentrations through their models, those different scenarios, and then they see how things behave. And when you go all the way back to emissions, there's a remarkable approximation that comes out that says the temperature change, at least over what economists call long horizons and geoscientists call modest horizons. Temperature change is roughly proportional to cumulative emissions, with there being this coefficient of which I'm called the cumulative carbon response. So this becomes a climate sensitivity measure. And so one way to do model comparisons is to run these simulations across models, look at the implied coefficient coming out of this, and then to see how much they vary across models. And so we're going to draw on some work that's been done of that type, just to kind of get going here. So here's the climate sensitivity uncertainty. It's that proportional relationship between cumulative emissions and temperature changes. This comes from a paper by McDougall, Swart, and Knutti. And what they're doing here is we're just tabulating in a histogram model output from a whole bunch of different models. Okay. So histogram is literally just tabulating outputs. One can attach those to subjective probabilities, but here, that says we want to treat all models exactly symmetrically. And in fact, we'll take that as a starting point. But the climate sensitivity, maybe the median value here is about 1.7. I'm not going to get into the units today, but just because of time constraints and the like. But what I want to convey here is great heterogeneity in that coefficient. While 1.7 might be the centering point, it can go all the way down to 1, or it can go substantially higher than 2, and still be well inside this histogram. So this climate sensitivity is unknown. Now I'm going to do a damage specification, a very simplified one that's come out of the environmental economics literature. It's ad hoc, but it's a simplification, but just to kind of illustrate the impacts of uncertainty. So it's going to be this damage process. It's going to capture the negative externalities on society, and I'm going to represent in log terms in this fashion. But there'll be some type of exogenous shifter. I'm not going to get into the details of that. The key thing is this lambda function. Lambda is going to have this kind of piecewise quadratic character to it. It's going to have this quadratic region up to little lambda bar, and then beyond lambda bar, there's going to be an additional curvature showing up. And this lambda bar is going to be set about 2 degrees Celsius relative to a baseline. So this lambda 2 plus gives a smooth alternative to what we think of it as a carbon budget. So it's already nonlinear damages coming from the lambda 2, and then the lambda 2 plus is going to potentially kick in more. Now, I can enter these damages proportionally into preferences, or I can have them scale equivalently consumption and or production. So I'm going to have the log of emissions showing up in preferences, but then I'm going to also think of this damages as either shifting consumption, so it's damage consumption, or else I can put it into the production technology equivalently. So here I'm just plotting out the proportional damage functions. There's a low damage model. These two models are going to track each other up into 2 degrees. And there's a literature coming out of climate science that says we should just impose a 2 degrees budget, and which was equivalent to like putting a vertical drop off here in the damage function at 2 degrees. We're instead going to imagine more smoother trade-offs. The low damage function is motivated by some work of Nordhaus, who uses damage functions that are in line with that red line there. Weitzman argued for more extreme damages. He appealed to uncertainty arguments for it, although he didn't really map them out with much clarity. But to put it in a more Weitzman-like specification, which we've also got this high damage function. Now notice up to 2 degrees, these functions are just tracking each other. They diverge. They're diverging after 2 degrees. And so this is a case where we don't, this is changes under which we don't have historical experience to just separate out these 2 different damage functions. Now I'm going to talk about uncertainty decomposition. I'm going to compute 2 different discount expected values of these social cash flows, these adverse social cash flows. One's going to form probabilities by simple averages. Another is going to form these ambiguity adjusted probabilities. And then I'm going to quantify the uncertainty of impact of uncertainty by comparing this by comparing these two, and argue that it could be quite impactful. So with this, we're deducing these as uncertainty adjusted probabilities. So if I gave you 2 damage functions, we're going to start off with an equally weighted version. And then what's going to happen is you're going to be making this conservative adjustment that's going to tilt it towards the high damages. And so the adjusted probability, the adjusted damage functions can look like the green line. Now we're also going to make adjustments in this climate sensitivity. And the way it's going to play out is as we get closer and closer to damaging the economy, the type of adjustments we're going to make are going to get much more substantial. So here we're going along a socially efficient path. So we're actually doing pretty well for 50 years just because we've imposed an optimal policy. But then by the time we're up to year 100, then there's these probability changes are kicking in a fairly sizable way. So think of the blue line as a smooth fitting of that Matthews approximation, and then the red is what's coming out of our computations in terms of the adjusted probabilities. And because we're doing this endogenously, the big adjustments are occurring as you make the economy more and more damaged. So the social cost of carbon is given by this blue line. So what's happening here is that's going to be increasing on you, and it's going to be even though it's kind of there's forward-looking piece to this, it's going to get bigger and bigger as you kind of move the economy closer and closer to the regions where the damages become more severe. And so this is the social cost of carbon worked out over a 100-year trajectory, which it becomes quite sizable as we start damaging the economy more and more. This has a hoteling-like flavor to it. Hoteling's work with a fixed resource stock also had a kind of an increase in the implied resource with a very similar trajectory. Here, it's not the fixed stock that's doing it; it's the damages that are putting in this hoteling effect. Now, how much of this are we attributing to uncertainty of the type that I just shown you? Those are uncertainty adjustments. Well, actually, quite substantially. So if we do that comparison of doing probabilities with and without the uncertainty adjustment, that's what shows up in this red line. And so we see these uncertainties as being really quite substantial. And so this model is highly stylized. I just want to show you these methods that these uncertainty adjustments can be important. I'm not saying this is the uncertainty adjustment, but from these illustrative calculations, they can be really quite impactful. Now, we also want to explore this nonlinearity, which I just imposed this so-called incredibly simplified Matthews approximation. That really doesn't do justice to geosciences. It's just some ad hoc approximation to facilitate model comparison. So think of there are two sources. I've got carbon in the atmosphere responding to emissions, and temperature responding to carbon in the atmosphere. So here I'm taking, I'm going to illustrate the nonlinear carbon dynamics. Climate scientists have done these pulse experiments. They run pulses through one of the standard models here of different sizes. And now if the carbon dynamics were linear, these lines here would all be right on top of each other. Because even though the pulse sizes are different, I'm rescaling these in order to convert them to fractions. I'm kind of basically dividing by the pulse size. And so for a linear model, these would be the same. And so what you're finding here is the bigger pulses, really the carbon that remains gets much more substantial. That this is because the impact of sinking the carbon and the like is affected by how much carbon you're actually putting there to begin with. And so that type of nonlinearity shows up, and that's present in the carbon dynamics. Remarkably, some economic approximations treat this as linear. Now, we want to take this all the way to temperature responses. Now, there's this Arrhenius rule that tells us that the temperature responses ought to be affected by the logarithm of, say, carbon in the atmosphere. And so that's an additional nonlinearity that shows up. And so without scaling, then these are the responses I would get to the different pulses. Not surprisingly, the bigger the pulse, the bigger the long-term impact here. But notice that that this is very flat and becomes flat after about 10 years. So whatever dynamics are playing out here, they're playing out at a fairly fast time scale. They're playing out over the time span of about 10 years. Now, remarkably, I'm going to take this figure and divide it by the pulse size. And now look, these things are like asymptotically right on top of each other. This is more evidence of this kind of the pulse counterpart of this Matthews approximation. Once you scale things by the size of the pulse, then this limit point is very much like the Matthews coefficient. There we said the centering point was about 1.7. For this particular model, is coming in about 1.6. Okay? So these two nonlinearities are kind of offsetting each other in ways that make this Matthews approximation kick in, and it's kind of a remarkable offsetting here in nonlinearities going on here. Now we need to take this further. We're going to have to now start inputting uncertainty in terms of these different sources. Moreover, the proportionality you can show breaks down if you have really large pulses, and the question, part of what we have to wrestle with is are the modest pulse experiments or large ones really the relevant ones for us? Then there's additional sources of nonlinearity coming through the permafrost. There's nonlinear feedback coming, arguments on the part of Gill and Zaliapin and Gill. We're currently collaborating with Gill to investigate these more seriously. And then, of course, I just showed you out these nonlinearities for one model. There's multiple sources of cross-model dispersion. So what we're doing now is trying to go back to these more primitive sources of the uncertainty and trying to figure out how important nonlinearity is and where the uncertainties are most important, coming through the carbon dynamics, coming through the temperature dynamics, or where. And we think the tools that we're bringing to bear here are quite interesting and can shed light on this. Now, we also need to engage in a richer economic model. Here there's no kind of possibility of shifting from fossil fuels towards renewable energy. We need to put multiple technologies on the table, a more green-friendly technology, and then put on the table, do we want to subsidize that or not? It's good to put on more nature-based type solutions, increasing sink capacity, enhancing resilience through biodiversity and the like. Resilience, adaptation, those static damage functions really sweep a lot under the rug. No doubt if we're changing the environment, changing the economic opportunities, there'll be dynamic responses, and how do we incorporate those? Now, all these extensions are absolutely important. In fact, I could add on to this geographic heterogeneity, which is also clearly absolutely critical to these discussions, policy discussions. All these extensions, while important, are going to just introduce additional channels with uncertain consequences. So the uncertainty is not going to vanish by ramping up this exploration. But it's going to allow us to investigate but we can also investigate how alternative policies can close the gap between actual prices and idealized notions of the social cost of carbon. So we find that to be kind of a useful metric as well. So anyway, this is just kind of work in progress. I think this is obviously a long-term project, not a single paper project, but one that I think asset pricing tools can be very, very insightful in thinking through the uncertainty consequences. With that, let me close with a quote from one of my favorite authors. Education is the path from cocky ignorance to miserable uncertainty. So what I'm going to argue here is that uncertainty can be challenging, it can be hard, but it's worthwhile trying to address it, and there's constructive ways to do it. Thank you very much, and I'm happy to entertain questions.
Well, all right. Thank you very much, Lars, for that fascinating and, of course, highly relevant talk. I appreciate it very much. I'll start a question. First, I thought at least halfway through that much of the things you were discussing or modeling approach probably could have been used in response to COVID in terms of model uncertainty in sort of the dealing with pandemic and the cost of the pandemic and so on. And I don't know if you thought about that.
Yeah.
And the other thing that I was going to ask is there a way to incorporate these model uncertainties into a tax policy? I think people agree that probably taxing carbon is the most efficient way of doing it. Is there a tax system or a tax methodology that would incorporate these uncertainties at all? Have you thought about sort of policy responses? Thank you.
Yeah, both actually. The COVID one is absolutely. The thing about COVID is that things are developing on a much more rapid time scale than, of course, climate change. But the same issues are there. If you look at a lot of the initial COVID model predictions coming out of epidemiology, there was lots of heterogeneity. It's clear there are uncertainty quantifications were missing something important. It's also the case that there were big changes, and so there's lots of kind of learning going on as well. So it's very, very clear case of model ambiguity there, and moreover, there was, when people talk about model projections off of those, sometimes they would talk about best guesses, and sometimes they would talk about possible bad outcomes, and those conversations would often not be terribly clear, and the nature of this research is, and sometimes you want to have an uncertainty trade-off, like they want to have trade-off considerations about, you know, the best guesses from what adverse things might happen. You don't want to go all the way on one or the other, but you want to figure out interesting ways to trade that off. So sometimes the model projections were not even clear exactly what they were, which numbers they were seeking to produce. So I do think that these type of tools can be very, very useful for that. Probably not for this pandemic, but maybe for thinking through future ones as we have to address them in the future, as we might confront them down the line. Your other question had to do with tax policy, and so I dismissed the Pigouvian tax as pie in the sky. Yes, I am very sympathetic to tax policy, and yes, this does produce tax implications. I mean, you know, literally in this case, the Pigouvian, it would tell you a Pigouvian tax that would repair this or formally address this externality. The tricky part of all that is we're dealing with one tax in isolation of the other ones, and to do a more serious job, one has to consider the interactions between the carbon tax and the other taxes in place. Moreover, it's very critical what you do with the tax revenue here. You know, if you're going to collect revenue on a carbon tax, it's also very socially important what you do with that revenue. You know, economists often, for simplicity, like to just remit it back to the people in the economy. The question is how you do that and what ways you do that as well. So yes, these tools can certainly help think about tax policy in a more realistic fashion for sure. But there's some there's some political economy questions that come up that I'm not an expert in, but I believe would be very important.
Thank you. If there is a question from panelists, go ahead. Otherwise, I have a couple of questions on the line. All right. Well, there is a question. Someone is asking that instead of nonlinearities, whether it would be possible, or maybe a better approach, to include jumps in the model. And the example given here is that Bangladesh, for example, could fall underwater and almost 1 billion people are displaced. So
so that's a very good point. Part of what climate science has talked about are so-called tipping points. You can think of those as a jump or as an extreme nonlinearity that plays out over a fairly small, over a fairly rapid time scale. So I kind of think of those two as a little bit hand in hand. But the issue about explicitly putting dramatic tipping points on the as part of the uncertainty, I think, is absolutely something that's valuable to explore. There have been some initial stabs at that in other contexts and other settings, and so there's definitely literature to draw from there and thinking about tipping point consequences. So, as I said, we're happy to do this. Our biggest challenge now is making all this stuff numerically tractable as well as conceptually interesting.
Thanks. We have another question. The role of technological innovation. Maybe perhaps even going to the policy, is there a way sort of maybe to have policies that would encourage more innovation in the right direction?
Sure. So here, I mentioned subsidizing green technology, but I guess one could roll that back into subsidizing R&D and the like along certain directions. And what are the potential benefits for doing that? So I think those are very interesting questions to explore. I think those are interesting policies to put on the agenda, and those are the type of questions we want to push this research in going forward. Because I would certainly agree with the question that these are potentially important policy questions to be exploring. So we think these tools can have valuable things to say, and but of course the challenge is to try to figure out to put in the credible uncertainty inputs as we're thinking about potential returns to R&D and the like, and to technological progress. And how much do we just rely on the market incentives, and how much should we engage in social subsidies in order to get it? And that's an interesting question, which we'd love to know more about.
Thanks. We have a couple of more minutes. I have a couple of questions, but I want to see if panelists have anything to ask.
So let me ask one question. Would you think we should encourage some kind of a market to back out these uncertainties, like some kind of options or long-term instruments which trade?
Yeah. Yeah, interesting question.
Something like temperature or carbon.
Yeah, very interesting question. So what I'm not talked about here is, I think these tools are also potentially useful for thinking about how investors, private sector responses to climate change, which is, and would there be incentives for would there likely be active participation in such markets and the like? So I think in the short run right now, the type of uncertainties faced by lots of businesses may be less about this fundamental climate change uncertainty that I'm talking about and more about policy uncertainty, which I think is currently is a big issue. What policies are we coming down the lines and when and the timing of all that? But I do think at some point also figuring out ways to address these type of uncertainties and maybe through market solutions could be very valuable. Lots of central banks, including, Carney was emphasizing this a lot when he was head of the Bank of England. Climate change could cause financial stability. I'm not sure that's my first order. I have lots of concerns about climate change. Financial stability may not be the first order concern that I have, but I think more generally that there's attached to that is what role, if any, should central banks be playing in climate change, and should they be trying to nurture markets that can help people help financial institutions better hedge against climate change uncertainties and the like, and then there may well be productive scope for that as well. As you know, one can envision markets and try to create them. My understanding from talking to Leo Malamed at the CME is that most markets, which they experiment with, fail, and including ones that economists think thought should be successful. So I'm not sure my speculation of what will work and not work should be all that trustworthy, but I do think it's certainly very interesting to explore whether there's kind of markets, we can't try to nurture markets to help the private sector cope with the uncertainties attached to climate change.
All right, I think we have time for one more question. Anything from the panelists, or I could ask?
Yeah.
Okay, go ahead.
I had a question. Do you, philosophically, do you think we're in the world of unknown unknowns, as our friend Nassim would like to call it, or we're in the world of known unknowns? You've done a lot of statistics with GMM and nonlinearity and all of that. What is your lifelong conclusion? What kind of world do we really live in? Do we live in the world where black swans do happen, and realistic to expect this climate change could explode someday in a way that we just don't anticipate?
Yeah, the unknown unknowns issue is the trickiest part of all this in some sense, I guess. For us to really get off the ground, we have to somehow bound the unknowns or something, or else if we get in this world where anything can happen and we're not going to even bound probabilities over it, then the question is, why do you get up in the morning? So we have to bound things somehow. And so how far you want to push on the other hand, it's no doubt that we're kind of, as things play out, we're kind of continually surprised by stuff that we thought we understood well. It turns out we didn't, and the like. So surprises are happening, and so I don't want to dismiss unknown unknowns. How to address them is the challenging part, I guess. So we're loading a lot in this potential model misspecification, and the unknowns are somehow put in there, but then we're addressing it in very special ways that may not be capture all the relevant unknown unknowns which you might have in mind. So I don't have the clean way to think about it. I guess I had a clean way to think about it, but I do acknowledge the issue. I think it's a very interesting one.
One last question, maybe as general as Sanjay's question. Have you had any interaction with policymakers who sort of understand and are interested in the results, or is it too early to sort of expect some reaction from policymakers?
I've had I've given a fair number of talks at central banks, not in the US, but in other countries. There's been lots of interest in the central banks in other countries in this. I think as I say, I'm not 100% sure central banks are the place we ought to be the ones on the front lines of addressing climate change, but they definitely have an interest and are anxious to communicate. I've had less interaction with other components of the policymaking community. Hopefully that can change in the future.
Hopefully. Well, thank you so much again, Lars. This was a fascinating, as I said, a highly relevant talk. So we thoroughly enjoyed it. We're going to have our break until 1 o'clock when Darryl Duffy will talk about the treasury market, but I'm going to keep the chat and everything open, of course, and panelists are more than welcome to exchange ideas. And of course, people on the question and answer can post questions and people can answer them. So thank you again, and I'll see you in about an hour and a half. Take care.